In the winter of 1932, the sky over the state of Connecticut was covered with a pale grey hue. Inside the Hamilton Standard plant in East Hartford, one could clearly hear the wind whistling through the tin roof and the deep metallic clang of steel striking steel. In the middle of the test chamber filled with the smell of oil and smoke, engineer Frank Walker Caldwell, 43 years old, stood before a gleaming steel shaft. Atop the shaft, an aluminum alloy propeller was being prepared for a test that most American engineers had predicted would fail. Caldwell's idea was considered a defiance of mechanical law, a propeller capable of changing its blade angle automatically while spinning at 2,400 revolutions per minute. From technical schools to the War Department, the reaction was the same. Engine experts at Curtiss-Wright insisted the variable pitch propeller was reckless. They claimed the centrifugal force at the blade tips would exceed 20 tons, enough to snap any control mechanism. No moving part can survive that stress, one engineer remarked at an American Aeronautical Society conference. Caldwell remained silent, his eyes behind round glasses fixed on the data chart. He believed the answer lay not in debate, but in numbers. "If the math works, the metal will follow," he wrote in his engineering notebook. 3 days later, a phone call from Boeing Field in Seattle opened the door to destiny. The Boeing Model 247, the most advanced passenger aircraft in the United States, was stranded at the Denver airport, unable to cross the Rocky Mountains. Its two powerful Pratt & Whitney R1000 340 engines were helpless because the fixed wooden propellers were optimized for only a single airspeed. At an altitude of 5,280 feet, the thin air prevented the aircraft from generating enough thrust. Pan American Airways sent an ultimatum to Boeing. "Fix it, or we're buying Douglas." The U.S. civil aviation industry was about to lose faith in domestic technology. Caldwell proposed an immediate test in East Hartford. He mounted the new propeller, a 3-blade hollow alloy design with an oil-controlled mechanism, onto the test stand. Engine oil pressure was channeled through the hollow shaft into a piston connected to a system of gears. As engine speed changed, the piston rotated the blades accordingly. In theory, the blades would adjust their pitch just like an automatic transmission in a car. The problem was that no one had ever dared allow a mass of metal to spin so fast while still containing internal motion. Caldwell watched the gauge needle reach 2,400 revolutions per minute, sweat forming on his hands. The shriek of the auxiliary wind fan merged with the deep roar of the engine. The propeller blades blurred into a white ring of light. When he adjusted the pressure valve, the rotation remained steady. Nothing exploded. The machine ran smoothly. He smiled. According to Hamilton Standard's report to Boeing dated the 15th of February 1933, the Model 247 equipped with the new propeller successfully took off. The aircraft climbed to 20,700 feet, crossing the mountains in harsh weather conditions. Cruising speed increased by 15 miles per hour, and fuel efficiency improved by 12%. Test pilot Eddie Allen telegraphed the company, "Constant speed propeller exceeds all performance claims. Recommend immediate adoption for the Tire United fleet." Silence filled the control room in East Hartford as the telegram was read aloud. Then someone clapped, and the applause spread throughout the factory. The press called it the impossible propeller. But Caldwell spoke not of miracles, he spoke of equations. In a short presentation, he described the principle: oil pressure from the engine moves the piston, transferring force to the centrifugal governor. As speed increases, the governor weights expand, adjusting the oil valve and changing blade angle to maintain stable RPM. The aircraft automatically finds a balance between thrust and speed. According to a report from the Massachusetts Institute of Technology in 1933, Caldwell's test model demonstrated the ability to maintain RPM within plus or minus 1% at all flight altitudes. Scientists called it mechanical intelligence for the first time. A device could optimize itself without human input. In December 1933, the news reached Washington. President Franklin D. Roosevelt awarded the Collier Trophy, the highest honor in American aviation, to Hamilton Standard Propeller Corporation for development of the controllable pitch propeller with particular credit to Frank W. Caldwell. At the White House, camera flashes burst as Caldwell shook the president's hand. He did not laugh loudly, only bowed slightly. A reporter asked, "What made you believe it could work?" Caldwell replied briefly, "Numbers don't lie." Oh. That same day, in the factory, young workers turned on the radio to hear the news. The announcer's voice echoed through the loudspeakers. The impossible propeller has been proven. A worker wiped his hands on an oil-stained apron, looked up at the steel ceiling, his eyes shining as if he could already see the shapes of airplanes that would fly farther and higher thanks to their very own hands. According to the records of the National Aeronautic Association, just 4 months after receiving the award, Hamilton Standard signed mass production contracts for the new propeller with United Airlines and Pan American. Transcontinental routes began to make economic sense. In an article in Aviation News in 1934, the editor wrote, "The success of the constant speed propeller is not just a technical victory, it is the birth of automatic flight control." At a technical conference in Detroit, Caldwell presented before delegates under the cold light of incandescent lamps. On the projection screen, curves of speed and torque intersected like 2 heartbeats. He pointed to the intersection and said, "Here, gentlemen, the propeller decides for itself." The room fell silent. That was the moment aviation stepped into a new era, and from within that silence, a mystery was born. It was no longer a question of centrifugal force, but a greater one. When machines begin to adjust themselves, what will humans still choose to believe in? Morning at Hamilton Standard in 1934, the East Hartford plant had changed completely compared to 2 years earlier. On the drafting tables, blueprints filled with numbers lay beside gleaming metal blocks. The once impossible propeller had stepped out of the laboratory and entered the production line. Each propeller assembly consisted of 47 components, machined with a maximum tolerance of 0.001 inch, a level of precision that many American industrial firms at the time had yet to reach. The lathe operators spent hours adjusting their cutting blades, each thread measured under a mechanical microscope. Under the fluorescent light reflected from the steel tables, the small components shimmered like shards of glass. A deviation no greater than a strand of hair could make the shaft vibrate at 2,400 revolutions per minute, destroying the entire system in its very first test. According to Hamilton Standard's internal records, Caldwell required all workers to sign inspection slips for each part before assembly. "Every measurement is a promise," he said in the Monday morning meeting. The young machinist stayed silent, knowing that the promise was not to the company, but to the sky ahead. Each completed propeller crate was packed and sent to the U.S. Army Air Corps testing base in Michigan, where a single demonstration could decide the future of American aviation technology. On the 21st of March 1934, at Selfridge Field, 2 Boeing P-26 P-shooter fighter aircraft stood side by side on the mist-covered runway. Both had Pratt & Whitney R-1340 engines, but one used a fixed-pitch propeller, while the other was equipped with Hamilton Standard's constant speed propeller. From the control tower, dozens of officers and engineers watched closely. Caldwell stood below, grey coat, notebook in hand. When the signal came, both aircraft started their engines, the sound of 2 different heartbeats. The first, with the fixed propeller, took 8 minutes 30 seconds to climb to 10,000 feet. The second took only 5 minutes and 40 seconds. At 15,000 feet, the new propeller's top speed reached 203 miles per hour, 16 miles per hour faster than its rival, with a ceiling of 34,500 feet compared to the old model's 28,000 feet. According to the test report by Lieutenant Carl Sparts to the Air Corps Command, the performance advantage is so significant that it represents a fundamental shift in combat capability. But in the conference room after the demonstration, the silence was not entirely admiration. A representative of Curtiss Wright Corporation noted in a memo, "This design is dangerously over-engineered. Too many moving parts, too many failure points." In an industrial culture that still worshipped the philosophy, "Simple is reliable," Caldwell's idea stood as the spear point between two schools of thought. As winter came, debates spread throughout the engineering community. Temperatures at combat altitude could drop to 60 degrees Fahrenheit, where hydraulic oil thickened and valves could freeze. How can a liquid system survive there? A test officer asked at Wright Field. The press was skeptical as well. Aviation Review wrote, "An engine's heart cannot depend on oil, for oil freezes." In conference rooms, the tapping of pens replaced applause. The doubt did not stem from data, but from fear, the fear of losing control to a machine that could adjust itself. Caldwell understood that. He did not respond with words, but with data. In a technical report sent to the War Department in 1935, he presented a continuous 500-hour endurance test under 50% higher load than combat conditions and 75% beyond the safe vibration limit. According to Hamilton's Standard Engineering Memo 1935-02, not a single part failed, and blade angle deviation after 500 hours was only 0.02 degrees. On the final page, Caldwell wrote simply, "Complexity does not equal fragility. It equals control." Oh. In a closed meeting in Washington, he brought a full-scale governor model. On a green felt-covered table, the small device about the size of a coffee can spun slowly as he turned it by hand, its silver metal weights glinting. "Gentlemen, this is not a complication." Caldwell said evenly, "This is precision." The lights shone down, the weights opened and closed with a soft click, like the breathing of metal. A colonel at the far end leaned forward to look closely. "It regulates itself?" he asked. Caldwell nodded. The room fell silent. According to the U.S. Army Air Corps Test Division Report 1936, the conclusion stated, "The Hamilton Standard Constant Speed propeller maintains rated RPM automatically and safely under all simulated flight conditions." For the first time in American military history, a mechanical system was authorized for autonomous operation. In the East Hartford plant, Caldwell walked past rows of running lathes, sparks from welding flashing brightly. It was said that he often stopped before oil drums, giving them a slight shake, then glancing at the pressure gauges, as if listening to the breath of the machines. One afternoon in 1937, when he returned to the test room, a replica of the propeller once called impossible stood proudly in the display hall. A young engineer asked, "Sir, what's next?" Caldwell replied, "Now we must make it unbreakable." That marked the beginning of hundreds of subsequent tests from maximum vibration to simulated impact, pushing every limit beyond imagination. According to the Engineering Review Journal in 1938, Hamilton Standard has achieved what others feared, a propeller that thinks. Journalists called him the quiet engineer. No grandstanding, no showmanship. Caldwell let the numbers speak for themselves. In the afternoon, light reflected from the aluminum body, and he wrote the final line of that year in his notebook. "The machine no longer needs my trust. It has earned it." And there, the mystery ascended to a new level, where the boundary between man and mechanical intelligence began to blur. When war broke out in Europe, the sky was no longer the realm of commercial flights, but the battlefield of speed and altitude. In 1939, Britain realized that the gap between itself and Germany did not lie in willpower, but in technology. Over the skies of France, the Messerschmitt Blei F-109 seconds climbed effortlessly, while British pilots struggled with the propeller pitch lever, their hands slick with sweat inside cramped cockpits. The Spitfire Minkai at that time had only a two-position pitch system, one for takeoff and one for cruising. To reach an altitude of 20,000 feet, a pilot needed 11 minutes and 8 seconds, over 2.5 minutes longer than their German adversaries. "At that altitude, we could see them climb away and we were stuck," pilot Douglas Bader wrote in his post-war diary. In the first dogfights, that difference cost hundreds of British pilots their chance of survival. At the British Air Ministry, meetings took place continuously. Reports from the front confirmed that the problem was not in the airframe or the Rolls-Royce Merlin engine, the fault was in the propeller. The technical officers looked across the Atlantic, where Hamilton Standard's constant speed propeller technology had already proven its automatic adjustment capability. In early 1940, the Air Ministry's Engineering Division signed an emergency contract with de Havilland Propellers Limited, a licensed manufacturer from the United States, to begin conversion trials. According to de Havilland Internal Memo 1940-06, Operation Hatfield was launched under conditions of absolute urgency. On the night of the 10th of June 1940, as the Luftwaffe began preparations for its assault on Britain, Squadron Leader Desmond Cook of Nodi 65 Squadron called the Hatfield plant directly, demanding, "Retrofit immediately 12 Spitfires. We cannot wait for approvals. We need altitude now," Cook said. Under the yellow glow of factory lights, hundreds of engineers and mechanics worked through the night. Each aircraft required 8 hours to remove the old hub, install the new hydraulic system, adjust the governor, and conduct pressure tests. The sounds of drills, hammers, and the smell of hot oil filled the hangar. At dawn on June 15, Cook personally piloted the first modified Spitfire serial number K9847. The aircraft rolled down the Hatfield runway, its tail lifting after just 225 yards. When the speed indicator moved into the green zone, Cook pulled back the control column. The Spitfire climbed like never before. According to data recorded in Flight Test Report number 12/1940, the time to reach 20,000 feet dropped to 7 minutes 42 seconds, and the service ceiling reached 39,000 feet, an increase of more than 7,000 feet over the previous version. Patrol duration extended by 45 minutes, thanks to improved fuel efficiency. Cook landed, stepped out of the cockpit, and looked toward the group of waiting engineers. "She climbs like she was born to fight," he said, his voice hoarse from the wind. According to the report of Air Chief Marshal Hugh Dowding, submitted to the Air Ministry on the 18th of June 1940, Operation Hatfield was considered the fastest and most critical mechanical conversion in RAF history. By the end of the month, the entire number 65 Squadron had been converted, and de Havilland expanded the process to other squadrons. "The Americans had the theory, but we had to turn it into survival," wrote Chief Engineer Harold Penrose in his memoir. "They not only replicated the design, but also had to relearn how to manufacture it. The problem was not the blueprints. The British had blueprints," aviation historian David Edgerton noted, "but not the production chain. The propeller required hydraulic oil with stable viscosity at 50 degrees Celsius, but that specific oil existed only in the United States, refined through multiple filtration stages to remove metallic impurities. Meanwhile, British factories were restricted by wartime materials. We built it right, but it didn't spin right," a de Havilland engineer recalled in a 1972 interview. In every factory, workers had to relearn how to machine hollow shafts, hand balance blades, and check pressure with mechanical gauges. The allowable tolerance was only 0.001 inch, an almost impossible figure under wartime conditions. Night after night, Hatfield glowed like an industrial torch. Amid the wail of air raid sirens, mechanics continued to work under the light of oil lamps. A young engineer named Alan Walker wrote to his wife, "We are racing the bombers in the dark, and each bolt we tighten might save someone's sky tomorrow." That line was later quoted in the de Havilland Museum as testimony to the race between engineers and time. According to the RAF Combat Evaluation Report September 1940, when the Battle of Britain reached its fiercest stage, 90% of RAF fighter aircraft had been equipped with American-style propellers. Spitfires and Hurricanes could now take off faster, climb higher, and maintain steadier cruising speeds than their German opponents. Pilot Brian Lane, one of the first to fly the upgraded Spitfire, wrote in his diary, "For the first time, we could climb with them, not chase them. In the air, war over Britain, that meant life itself." According to the British Air Ministry summary, November 1940, the survival rate of RAF pilots in air combat increased by nearly 40% after the propeller system upgrade. The Statistical Office called it the most decisive mechanical upgrade in modern warfare. Those cold numbers concealed thousands of hours of labor, hundreds of night shifts, and the calloused hands that turned an American mechanical mystery into a British weapon. By the end of the autumn of 1940, the new Spitfires flew over London with a different sound, the engine tone deeper and steadier, like a perfect mechanical symphony. In the BBC evening broadcast of September 30, the announcer's voice declared, "Britain now fights with machines that think." And there, the mystery had spread worldwide, not merely as an invention, but as a symbol of faith in human intelligence amid the storm of war. Before moving on to the next part, if this story touched you, please like and share it so more people can see it. Share your thoughts in the comments. Every word from you is the motivation for us to create more great videos. In 1941, the United States had not yet officially entered the war, but the factories of Hamilton Standard were lit around the clock. From a facility of only 800 workers, the company expanded into a massive complex of 22,000 employees, operating 3 shifts per day. The hydromatic propeller was no longer the creation of a small group of engineers. It had become a symbol of American industrial power. According to the Hamilton Standard Production Log 1942, the production line reached a capacity of 12,000 propeller units per month, an unprecedented figure in aviation history. The sound from the factory thundered like the heartbeat of a nation preparing for war. In the assembly hall, hundreds of raw aluminum blocks were turned, milled and polished until they shone silver bright. On the wall hung a slogan, "Every blade saves a pilot." Caldwell walked through the rows of machines, coat stained with oil, eyes fixed on every spinning shaft. "They must all spin the same way," he told the shift supervisor. Each propeller was a self-regulating micro-mechanical system, and to make thousands of them function in harmony, Hamilton Standard had to redefine the entire concept of mass production. According to the War Department Industrial Integration 1942, 3 major civilian corporations were mobilized to create a new manufacturing ecosystem. Frigidaire, once a refrigerator producer, was assigned to build the hub, the propeller's center, where oil pressure flowed through the hollow shaft. Remington Rand took responsibility for fabricating the Governor, a centrifugal speed control unit smaller than a coffee can yet containing more than 50 intricate parts. Nash Kelvinator, a home appliance manufacturer, switched to producing pistons and hydraulic valves. The entire United States became an industrial network bound together by Caldwell's blueprints. A young engineer at Remington Rand recalled in his 1975 memoir, "We built Governors the way others built watches." At Frigidaire, female machinists sat along the line, fitting rubber seals onto steel shafts, their hands trembling slightly under the precision requirement of 0.001 inch. Each component assembly, once completed, was sent by rail to East Hartford, where Caldwell had set up the central inspection system. In a white room filled with pressure, temperature, and vibration gauges, the propellers were tested under the harshest conditions. According to the Hamilton Standard Quality Manual 1942, the company's QC, quality control process, was the first automated model in the aviation industry. Each propeller unit was placed in a testing chamber, exposed to temperatures from 60 degrees Fahrenheit to plus 140 degrees Fahrenheit, and subjected to vibrations exceeding 75% of normal operating limits. Electromagnetic instruments recorded every fluctuation in oil pressure and blade angle, printing data on meters-long paper strips. After each unit passed inspection, the chief engineer was required to sign directly on the propeller's body before packaging. Every signature was a vow, Caldwell told the management team. That precision made Hamilton Standard the technical lifeline of America's war effort. According to the United States Office of Production Management report, December 1942, nearly 60% of all U.S. teen military aircraft used Hamilton Standard propellers. The Frigidaire and Remington Rand lines operated 24 hours a day, guarded like defense installations. It was no longer about building parts, wrote Chief Engineer Arthur Carlson. It was about synchronizing an entire nation's machinery. but with scale came a shadow. In the summer of 1942, as the United States entered full mobilization, the government ordered a 30% increase in production. To meet the target, Hamilton Standard had to recruit thousands of new workers. Many were farmers, seamstresses, and students who had never touched a lathe. Training time was cut to only 2 weeks. Caldwell objected, but pressure from the War Department was relentless. "They need the blades now," an official said, and the production line ran faster. Inside the plant, the hammering of metal sounded like explosions. The temperature rose above 100 degrees Fahrenheit, and oil vapor hung in the air like fog. One engineer wrote in his diary, "The machines no longer rest, neither do we." As speed increased, so did error. According to the Factory Audit Report 1942 Q3, the assembly deviation rate doubled compared to earlier in the year. Some governors leaked oil. Several shafts were imperfectly balanced, Caldwell noticed during a night inspection. He stood silently before the conveyor, watching the crates of propellers being sealed, the glow from the forge reflecting off his glasses. "Speed is the enemy of precision," he wrote in a note to the board. But war would not wait. After Pearl Harbor, orders from the U.S. Air Corps surged. The entire nation shifted to a wartime footing. People began to call Hamilton Standard the beating heart of the skies. Caldwell understood that the mystery of the propeller was losing its original purity as it passed from the hands of engineers into the machinery of mass production. According to the National Defense Manufacturing Record 1942, in the final quarter of the year, Hamilton Standard shipped 35,000 propeller units, a number far beyond all projections. But alongside it came a 3.8% defect rate, a warning clearly stated in the report. Caldwell looked at the dry figures, knowing that what he had built with meticulous care was now being tested by the very scale he had created. On the last night of the year, he returned to the test room, where the original Boeing 247 propeller still hung on the wall. The fluorescent light reflected on the aluminum surface, casting a faint halo. He touched the shaft gently, feeling the cold, damp metal. "Perfection can't be multiplied," he whispered, as if reminding himself. Outside, the factory whistle sounded the end of the shift. The clang of metal echoed in the dark, like the laboured breathing of a machine that had surpassed its own limits. And within that echo, the mystery took on a new form, from the creation of one man to the assembly line of an entire nation, where every revolution carried both the power and the peril of modern industry. In the autumn of 1943, when war had turned the skies of Europe into a labyrinth of smoke and fire, America seemed to have achieved perfection in weapons production. Each day, hundreds of B-17 flying fortresses left the factories, equipped with hydromatic propellers verified through hundreds of precision tests. Hamilton Standard announced a defect rate below 2%, an achievement the press called the triumph of precision. Caldwell read the words of praise in silence. He understood that industry was a giant organism, and sometimes it concealed flaws no one could see. On the morning of the 14th of October, 1943, the formation of B-17 seconds from the 8th Air Force took off from England to bomb Schweinfurt, the industrial centre of Germany. Among them was B-17 serial number 42-31041, nicknamed Hell's Angels. The 9-man crew, commanded by Lieutenant William Parker, departed at 7:25 a.m. According to Mission Log 8th Air Force, the 14th of October 1943, the flight proceeded normally at first. Upon reaching the target area, anti-aircraft fire intensified and a shell fragment pierced engine number 3. Co-pilot Jack Morgan recorded in the radio log. "Engine 3 hit, oil pressure dropping." Following protocol, they activated the feathering mechanism to turn the propeller blades parallel to the airflow, reducing drag and maintaining balance. But propeller number 3 did not respond. Instead of holding position, it reversed into the airstream, creating massive resistance. Airspeed dropped 40 miles per hour, and the aircraft rapidly lost altitude. Attempts to regain control failed. Parker ordered, "Bail out, But it was too late. At 12,000 feet, the right wing snapped. The Hells Angels spiraled, caught fire, and crashed into the Bavarian forest. All 9 crew members were killed. The final report contained a single line. Feathering mechanism failed due to oil freezing. The news shook the War Department. Within 2 weeks, 3 similar incidents were recorded. A total of 47 propellers from the same production batch showed signs of oil pressure loss at altitudes above 30,000 feet. A technical investigation was launched with unprecedented urgency. At the Hamilton Standard Laboratory, engineers dismantled every component and examined each oil line under microscopes. Inside the oil tubes, they discovered a faint white crystalline residue. Chemical analysis identified it as paraffin and metallic dust mixed in the hydraulic oil. According to Technical Report number 27 over 1943, the contamination originated from a subcontractor in Ohio, where the oil had been bottled hastily without cold filtration. At 30 degrees Fahrenheit, the impurities crystallized, blocking the pressure valves and preventing the propeller from feathering. When the report reached Caldwell, he remained silent for a long time. In his brightly lit office in East Hartford, he wrote in his notebook, "The machine is perfect, but the chain is not." On November 20, he flew to England aboard a military transport. At RAF Thorpe Abbott's base, he met pilots of the 8th Air Force repairing surviving B-17 seconds. A grease-stained engineer showed him a fractured propeller hub. "It wasn't your design, sir. It was the oil." Caldwell nodded, his eyes heavy. He knew the mystery of this failure did not lie in design, but in a supply chain stretched thin by war. According to the records of the U.S. Army Air Force's Investigation Board, Caldwell stayed in England for 3 weeks. He traveled across bases, speaking with pilots, engineers, and maintenance crews. One evening, in an aircraft hangar under the dim yellow light, he told a group of engineers, "We built a mind that could think, but forgot the veins that feed it." The quote was later included in the official report sent to Washington. It was both an admission and a warning. Upon returning to the United States, Caldwell demanded an immediate redesign of the entire hydraulic system. The updated model featured 2 independent oil circuits and a mechanical backup mechanism, allowing the propeller to feather even if pressure was lost. He also required all propellers to undergo environmental tests from 60 degrees Fahrenheit to plus 140 degrees Fahrenheit, along with vibration endurance 75% above combat standards. Every batch of hydraulic oil was to be sampled, frozen, and thawed at multiple temperature levels to detect impurities. According to Hamilton Standard Reliability Memo 1944-01, after 6 months of implementation, the propeller failure rate dropped below 1%, even lower than Air Force specifications. The War Department ordered nationwide adoption of the protocol, naming it the Redundant Hydraulic System Protocol. Journalist Ernest Gann, in his 1944 Saturday Evening Post article, described Caldwell as the engineer who turned disaster into discipline. The B-17 seconds soon returned to the European skies, taking off into freezing fog without fear of their feathering systems freezing solid. A Hamilton Standard engineer later recalled the night Caldwell walked through the factory after returning. He didn't speak. He just touched the new valves lined on the table, one by one. Outside, trains loaded with propellers departed into the darkness, red lights reflecting off the aluminum surfaces. In the June 1944 report, the Army Air Force's Technical Division noted, "No further feathering failures reported in European theatre since January." The mystery had been broken, but its price was 9 lives. Caldwell kept a copy of the investigation report on his desk for the rest of his life. In an internal meeting, he once said, "Perfection is not an end. It is a moving target." The mechanical intelligence he had created had learned to repair itself, and America had learned how to sustain that intelligence within a vast system. By the end of 1943, as the new B-17 seconds flew across the North Sea, people said they could hear something different in the engine sound, the smooth, even rhythm of the propellers, flawless and synchronized. According to the 8th Air Force After Action Summary, The mission completion rate of B-17 squadrons increased by more than 20% in just 3 months. Amid the roar of wind and fire, mechanical intelligence had restored faith. And in that moment, over the snowy skies of Europe, the B-17 seconds glided through the pale dawn, as if the mystery had been cleansed not within the metal itself, but in the hands of those who dared to admit mistakes and rebuild the world. In January 1944, after radical technical improvements following the Hells Angels disaster, the skies over Europe gradually belonged to the Allies. The B-17 and B-24 squadrons of the 8th Air Force began conducting daylight bombing runs deep into German territory. In the technical report, U.S. Army Air Forces Operational Data, January 1944. The figures revealed a clear leap forward. Each B-17 Flying Fortress could now fly 50 miles per hour faster, reach altitudes 8,000 feet higher, while consuming nearly 15% less fuel than previous versions. The hydromatic propeller system, with its ability to automatically adjust blade pitch, had turned an inert block of metal into a system capable of adapting to every layer of air, every change in the engine, every breath of wind at 40,000 feet. According to the technical briefing, 8th Air Force 1944, superiority was no longer a claim for conference rooms. It was manifest in every battle. Over Berlin, while German early warning radar was still analyzing signals, the P-51 Mustangs appeared like silver arrows. Thanks to the self-adjusting propeller, the Mustang's cruising speed was 30 miles per hour faster than the Bf-109 and its ceiling 5,000 feet higher. American pilots could now decide when to fight and when to disengage, a privilege never before possible. "It climbs like thought itself," said Lumt George Preddy after the Battle of the 18th of June 1944, when he downed 3 German aircraft in just 8 minutes. In the Pacific, the mechanism created another tactical revolution. The P-47 Thunderbolt Heavy, once dismissed as too slow to face Japan's A-6M0, has now achieved a 40% faster climb rate. When the Zero began to turn, the Thunderbolt was already above it, nose down, attacking. "The secret was in the prop," recalled Lieutenant Francis Gabreski. "It adjusted before I could even think." According to the Pacific Air Command Combat Report 1945, the P-47's air combat win ratio reached nearly 3-1, a figure that had been only a dream for the U.S. Army Air Forces in 1942. But the deeper impact was not in speed, it was in the psychology of the pilot. Before, aviators had to manually adjust the pitch while maintaining balance and avoiding engine overspeed. A small mistake could cause an engine explosion or a total loss of thrust midair. When automation was perfected, they could focus entirely on combat. "It was like flying with a second pilot in the engine," wrote pilot Robert de Haven in his memoir. Continuous automatic adjustments made the aircraft feel lighter, more responsive. Every movement on the control stick became precise, no longer slowed by mechanical lag. According to the post-war study, Aviation Psychology Division Report 1946, pilots' neural fatigue levels decreased by nearly 30% on missions lasting more than 6 hours. The propeller could listen to the engine, knowing when to change its angle to keep the RPM steady. This automation was not just a technical convenience, but the first step toward intelligent mechanical thinking, where machines began to share responsibility with humans. At an internal meeting in Washington in 1944, a senior officer told Caldwell, "Your propellers changed the sky." He replied simply, "We just let the machines think for us." The phrase spread among aviation engineers as a new philosophy. Efficiency came from trust in data and systems. As the war entered its final year, the scale of hydromatic propeller technology reached global proportions. According to the U.S. War Production Board, Summary 1945, more than 530,135 propeller units had been produced for combat and bomber aircraft, from the B-24 Liberator to the P-38 Lightning, from the P-47 to the B-17. Every American aircraft, from Europe to the Pacific, bore Caldwell's design. In factories across Connecticut, Michigan, and California, The conveyor belts never slept. Workers changed shifts to the blare of steel whistles, and shining propeller blades lined the floors like the swords of a mechanical army. According to the Strategic Air Force's Evaluation 1945, Allied technical superiority lay not only in quantity, but in the quality of each machine. Bombers could fly higher, farther, and beyond the range of enemy anti-aircraft fire. From altitudes above 30,000 feet, bombing raids on the Ploesti oil fields and the Ruhr industrial zone became more accurate than ever. "We could stay up there, above their reach," recalled pilot Harold Stovall. "Our props never failed." By August 1945, when the war ended, the U.S. Army Air Forces released a report titled Impact of Variable Pitch Technology on Air Superiority. The final figure was staggering. The automatic propeller system had saved approximately 15,000 aircraft from being shot down or forced to crash, land due to engine failure. According to the Army Air Force's 1945 summary, the survival rate of bombing missions increased by 18% compared to 1943. In a world ruled by probability and death, that number was a miracle. On the 2nd of September 1945, at Tokyo Bay, as Japan's surrender was signed, B-29 superfortresses circled overhead, all equipped with propeller technology derived from Hamilton Standard's hydromatic system. In the dim sunlight, their blades spun into silver circles, reflecting on the sea like giant clocks marking the dawn of a new era. Caldwell was in his East Hartford office. He heard the news over the radio, one hand resting on the old Boeing 247 blueprint. From that first test in 1933 to victory in 1945, it had taken exactly 12 years for an impossible idea to become the foundation of global triumph. He looked out the window, where thousands of workers were leaving their shifts, the afternoon light slanting across the rooftops, the factory whistle echoing long and low. In that moment, every sound seemed to fade, leaving only the whisper of wind through the propeller on the test stand. And in that silence, the Luftwaffe died. In the spring of 1946, as the smoke of war cleared, the Hamilton Standard factory in East Hartford still glowed with light. The production lines that once built thousands of hydromatic propellers now serve civil aviation. On the office walls, charts and the slogan, "Quality is not inspection, it is discipline," reflected a new focus, the art of precise control. According to the U.S. Bureau of Standards Report 1946, from Hamilton Standard's inspection methods, American industry developed statistical quality control. Every variable vibration, pressure, blade angle was recorded and analyzed. Caldwell called it the logic of trust. Believe in data, not feeling. Engineers learned to read charts like doctors reading heartbeats. A small deviation could save a life. At the 1947 ASME conference, Caldwell's speech, Learning from the Machine, stated, "The propeller taught us to measure, not to assume." The quote marked a turning point in U.S. engineering. From Ford to Boeing, factories adopted statistical production. An error rate below 1% became known as Hamilton Standard precision. By 1948, oil pressure and automatic control technology spread across industries. The automotive field used it to create automatic transmissions. Shipbuilders refined hydraulic governors. Machine tools adopted centrifugal balancing systems. A once over-engineered device had become the backbone of modern engineering. The Economic Transition Bureau 1950 reported that self-adjusting hydraulic systems contributed over 12% of U.S. industrial GDP, about $25 billion. Thousands of Hamilton Standard engineers joined new industries. One, Arthur Carlson, wrote, "We left the war, but the war left us with precision." At the Smithsonian, the Boeing 247 propeller rests behind glass. Its plaque reading, "This was the first machine that thought mechanically," historian David Mindell noted. Caldwell's design marks the moment when machines began to anticipate rather than react. That concept, mechanical intelligence, opened a new era. In the MIT Lecture Archive 1952, Professor Harold Hazen asked, "Can a machine think in numbers?" Students answered. The propeller already had, 2 decades before. Caldwell died in 1963, aged 74. At his funeral, colleagues placed a piece of hydromatic propeller aluminum on his grave. One whispered, "He gave wings a brain." By 1965, hydromatic systems powered over 60% of civilian aircraft. Hamilton Standard produced 200,000 hydraulic components yearly, expanding into missile and aerospace work. Beneath Caldwell's 1,933 photograph at headquarters, the motto read, "Perfection is measurable." From war tests to global industry, preserved archives told one story: the rise of mechanical intelligence. And today, when pilots take off in computer-controlled cockpits, they still hear that same sound. The propeller adjusting to the wind, the enduring heartbeat of an idea born in 1933. The propeller has been decoded, yet the mystery Caldwell left behind endures. The question of artificial intelligence's limits, the boundary between man and machine. Each time the engine starts and the propeller begins to spin, the numbers from those old data sheets seem to come alive again. They remind us that perfection is never static, it keeps turning, like the endless motion of the invention that changed the world. Thank you for following the story of Frank Caldwell and the hydromatic propeller, a seemingly small invention that shaped an entire global industry. From a modest workshop in East Hartford to the skies over Berlin, from drawings on paper to the automated systems that launched the age of intelligent engineering, that legacy still turns, inspiring those who dare to believe in the power of thought and discipline. We are committed to bringing you the finest content, true stories of engineering, history, and humanity, where every detail, every number, tells the journey of intelligence. Don't forget to subscribe to the channel to follow more battles ahead.